Okay.
Okay. So, Ugo, please share your presentation and.
Okay. Do you see it?
We see it. Okay. Go ahead.
Okay. Hello everyone, I am Ugo Niccolo Di Carlo, and I'm going to talk about the results I got through my PhD thesis. And the title of my thesis is Black Holes in Young Star Clusters. So let's start with a quick overview of all my interests and the results I got through my PhD. My main interests, as you can see, are the dynamics of star clusters, and in particular the formation of massive black holes in star clusters and the formation of gravitational wave sources. During my PhD, I had the opportunity to dive in many different areas which concern these topics. But for today, I will just focus on the main result on which I worked more, which are the star cluster dynamics and its effect on gravitational wave sources, the formation of black holes in the penny-stability mass gap, and the formation of intermediate mass black holes in young star clusters. So, as you probably know, we recently detected the very first gravitational wave signal from the merger of a binary black hole. And since then, this detection revolutionized our view of many areas of astrophysics. Thanks to the LEGO and Virgo collaboration, we were able to detect 10 binary black holes and 1 binary neutron star thanks to observing runs 1 and 2. And thanks to observing run 3, we got more or less 40 low-Alzheimer rate triggers. These detections, some of which are shown in this plot, represent the merger of compact object binaries. Mostly, we detected the merger of binary black holes. And as you can see, we found out that very massive black holes exist. And this revolutionized our view of stellar evolution because now we know that very massive black holes can exist with masses up to 160 solar masses, more or less. And how do these binary black holes form? There are mainly two proposed formation channels for such binaries. The first one is isolated binaries, in which two stars form from the same molecular cloud. They evolve bound together, and they eventually can evolve into black holes, forming a binary black hole, which can then maybe merge and emit gravitational waves. And another proposed scenario for the formation of binary black holes is the dynamical one, in which the binary black holes forms and evolves inside the star cluster or a dynamical active region, and dynamical processes can affect its evolution. So what are these star clusters? Star clusters are defined as self-gravitating systems of stars, and we mainly observe 4 different types of star clusters. First of all, globular clusters, which are the oldest one. They have an age which is comparable to the age of the universe. They contain from 10 to the 6 to 10 to the 7 stars. And you can see on the top panel on the right, an image of M4. This is a globular cluster. You can see its symmetrical structure, which is more or less spherical. Then we also observe open clusters, which are younger than globular cluster. They're not dense and they contain few stars, from 10 to the 2nd to 10 to the 4 stars. Then we also observe nuclear clusters. This is a very peculiar type of clusters because they reside in the center of galaxies. So they can have a supermassive black hole in the center. They're very dense and massive, and they contain up to 10 to the 8 stars. And finally, young star clusters, which are very young, but they are dense and massive. They can have from 10 to the 3rd to 10 to the 6 stars. And here on the bottom right, you can see an image of the Arches cluster, which is a young star cluster near the center of our galaxy. As you can see, its structure is different from the globular cluster on the top because it's much more asymmetrical and clumpy. So why did I chose to study young star clusters and the formation of binary black holes in young star clusters? First of all, because the detection by LEGO Virgo raised up the problem of the sources, of the origin of the sources which emit gravitational waves. So we need to constrain where and how such binary black hole form. Then I chose young star clusters, which are small, because they may be small, but they also make up the majority of star clusters in the universe, and so their cumulative effect may be very important. We also know that massive stars, which are the progenitors of black holes and compact objects, form mainly in clustered environments. And finally, the effect of dynamics may be very important for binary black hole formation. And to better show what is the effect of dynamics, I will show you two of the possible processes which can affect binaries inside a star cluster. So in the top panels, you can see the hardening process. First, you start with a binary black hole and a third star flies by. And as a result, the star extracts some energy from the binary, gaining some velocity, and the binary black hole hardens, meaning that its orbit will shrink. And eventually, it will merge because shrinking gravitational wave emission becomes more efficient, and so this binary can merge more easily. On the bottom panels, on the other hand, you can see the exchange process. Here, for example, we start with a binary made up of a black hole and a star, and a third black hole flies by. As a result, the star is ejected from the binary, and the black hole replaces the star. So a new binary forms, and this time is made up of two compact objects. Now, to better show how these processes work, I have produced an animation, which you can see here. This animation comes from a real simulation of three bodies. It was performed with the code RChain. So the simulation of the gravity of these three stars is very accurate. And it also includes post-Newtonian relativistic terms. So here we start with a binary made up of a star and a black hole. And you can also see that there is a neutron star, which is the blue one, which is trying to perturb this binary. In fact, as you can see, each time this neutron star flies by, the semi-major axis of this binary changes. For example, now you can see that it becomes much more wider, and it eventually, the exchange will happen, and a new binary made up of two compact objects forms. And this binary may be important for gravitational wave emission. So how did I study this problem? Well, I made use of numerical simulations of star clusters. I mainly use two codes. One is Embody6++ GPU, which is the code that simulates the gravity between two stars. And then I also use MOBSE, which is the code used to perform the stellar evolution of stars. And during the first part of my PhD, my job was to couple these two codes in order to perform state-of-the-art accurate dynamical simulations with accurate and up-to-date stellar evolution as well. And in this animation on the right, you can see the animation of one of the many simulations which I have performed during my PhD. Now let's have a closer look at these two codes. On the left, we see that MOBSE stands for Massive Objects Binary Stellar Evolution. It is an upgrade of the very famous BSE, it includes recipes for the evolution of massive objects. It has new updated core collapse supernova models. It also includes recipes for the pairing stability and pulsational pairing stability supernova. It includes the formalities for binary evolution processes, for example, like Roche-Loeb overflow or the common envelope. And it also has updated recipes for stellar wings, especially for massive stars. On the right side, we can see that the code I use for gravity is Embody6++ GPU. This is a direct embody code, meaning that each particle feels the gravity exerted by each other particle. The integrator uses a fourth-order Hermite integrator. It also includes some numerical tricks to improve the accuracy and the performance of the code, like the block time step and the KS regularization. And finally, it also includes GPU parallelization to increase the performances. But what are the initial conditions that I use for my simulations? First of all, the mass of the simulated star cluster was extracted by a distribution which goes with m to the -2 from the mass cluster function from Della 2003. So I simulated more less massive clusters and more massive clusters. The star clusters I have simulated have a fractal distribution, spatial distribution of stars to mimic the clumpiness of the star-forming regions. And the binary fraction, the initial binary fraction of massive stars was 1, meaning that all the stars with mass larger than 5 solar masses were in a binary system in the beginning of my simulation. And this is a very important feature of my simulation, because we know that the binary fraction is a huge bottleneck for this type of simulation, because binaries have a larger cross-section, and so simulations with large binary fractions take more time. In fact, in previous work that were made, either the binary fraction was very low, close to 0, or the number of simulations was very low. But actually, during my PhD, I was able to perform more than 10 to the 4 simulation. And I also explored the parameter space. In fact, I simulated star clusters with different metallicities, but also with different initial ready and other stuff, in order to check what is the effect of dynamics on the gravitational wave sources. I have also produced a control sample of 10 to the 7 isolated binaries with the same exact stellar evolution. So why did I use the fractal initial conditions? As we can see from this picture of R136, which is a very young cluster in the Large Magellanic Cloud, the structure of the stars, the spatial distribution of the star is not symmetric. It's very clumpy, and stars are distributed not evenly. In fact, star-forming regions are very asymmetric, and the gas distribution is important. It would be nice to perform hydrodynamical simulations along with dynamical simulation, but this would be too computationally expensive, especially to produce a statistical catalog of gravitational wave sources. So here you can see different degrees of fractality that you can assume for your star clusters, going from extreme levels of fractality to basically no fractality. And for my work, I chose this fractal dimension, which comes from this work from Portegues-Suar 2016, in which he compares observations with embodied simulations of star clusters, and he claims that this is one of the most likely fractal dimensions for young star clusters. Okay, so now let's start with the main results that I got through my PhD. And we start talking about merging binary black holes and the comparison with the isolated binary formation scenario. Okay, here in this plot, you can see the distribution of the black hole masses that formed in my simulations. On the top panel, you can see all the black holes that formed in my stellar cluster simulations, so the ones affected by dynamics, while on the lower panel, you can see the black holes formed in the isolated binary simulations. As you can see, the maximum mass of the formed black hole is dramatically affected by dynamics. In fact, in this picture, you can see only black holes that form up to 150 solar masses, but I had black holes with masses up to 440 solar masses, roughly. And I will talk about them later. The vast majority of the black holes, on the other hand, since we have a logarithmic scale on the y-axis, is the same. But the maximum mass is dramatically affected. Not only on the distribution of all the black holes, but also on the red one. Red distributions show the black holes in the merging binary black holes. And we can see that the maximum mass of black holes in merging ones is affected by dynamics as well. And now let's have a deeper look at these merging binary black holes, starting from the total mass of the merging binary black holes, where the total mass is simply defined as the mass of the primary black hole plus the mass of the secondary black hole. Here you can see the distribution of the isolated merging binary black holes, picking up between 20 and 30 solar masses. And now let's see what happens if we add the dynamics to this picture. So here you can see three distributions which come from dynamics. First of all, let's look at the red one, which is just the distribution of all the merging binary black holes which form in my star cluster. As you can see, the total mass of the merging binary black holes is much larger than the one in isolated merging binary black holes, going up to 120, 130 solar masses. Not only this, but also the peak is shifted. Now I have divided this distribution into two subsets, the orange and the blue one. The orange one represents the merging original binary black holes, which are the binaries which were in the initial conditions of my simulations, while the blue one represents the merging exchanged binary black holes, which are the binaries which form thanks to dynamical interactions. As we can see, the blue one, the exchanged ones, the effects of dynamics are much more evident in the blue distribution. But on the other hand, these effects are also visible on the orange one. So original binaries are affected as well. In fact, we can see that the peak is shifted between 30 and 40 solar masses. And now let's also have a look at what is the mass ratios of the sources. The mass ratio is simply defined as the mass of the primary, the mass of the secondary black hole divided by the mass of the primary black hole. This means that a mass ratio of 1 will mean that the binary will have equal mass black hole, while approaching closer to 0, the masses of the black hole will be much more uneven. So what we can see here is that in the isolated case, the merging binary black holes tend to have much more equal masses than in the dynamical case. And in this case, you can see that the merging exchanged binary black holes are more affected by dynamics, like for the total mass. You can see, in fact, that the isolated scenario can go down to 0.2 at best, while thanks to dynamics, we can approach much more to 0. And now let's also have a comparison of my sources with the detections we got from Live and Virgo. Here in this plot, we have the mass of the primary versus the mass of the secondary black holes. The different colors represent different metallicities, and the yellow stars represent the detection from O1 and O2 from the observing ground 1 and 2 from Live and Virgo. The open circle represents the original black hole, while the field symbols represent the exchanged ones, and the gray shaded area represents the distribution of the isolated binaries. So, as we can see, the merging binary black holes in my dynamical simulations tend to stick to the isolated ones, but there are a lot of merging binary black holes with much larger masses and with smaller mass ratio. In particular, we can see that the more massive ones and also the ones with a smaller mass ratio tend to all be from metal poor star clusters and to be exchanged ones. And if we compare our merging binary black holes with the detections, we also see that some events, like this, which is one of the most massive ones we got so far, and this, which is the first unequal mass merger, can be matched only by merging binary black holes in metal poor exchanged and by exchanged binary black holes. Okay, now how many binary black holes form and what is the efficiency of the formation of merging binary black holes in my star clusters? To analyze this, we have defined this quantity, which is called the merger efficiency, which is basically defined as the number of merger divided by the total simulated mass we have. So in this plot, we can see for different metallicities the merger efficiency. The symbols are from my dynamical simulations, while the dashed line is from the isolated binary evolution. While we see that at lower metallicity, the merger efficiency are similar and comparable to the isolated ones, we'd also see that at solar metallicity, there is a very huge boost of the merger efficiency, which is larger than 2 orders of magnitude. And we think that this effect may be because at solar metallicity, you hardly have any merging binary black hole in the isolated scenario. And in this case, dynamics can help thanks to the hardening and to the formation of merging binary black holes. In this lower metallicity, on the other hand, dynamics can also lower the number of possible mergers thanks to the breaking the binaries, thanks to dynamical interaction and thanks to softening the binaries after 3 body encounters. Okay, now let's move in the second part of the results which I got through my PhD. Now I will talk about black holes in the pairing stability mass gap. So first of all, let's start with a quick overview of what is a pairing stability supernova. This is a peculiar process which happens if after the carbon burning, the star has an helium core which is more or less between 30 and 135 solar masses. So what happens is that in very massive stars, pair production can happen because you have very energetic gamma ray photons that can interact with the nucleus and produce couples of positrons and electrons. This produces a lack of pressure which cannot sustain the strong gravitational infall of the star, and so it produces a dramatic collapse through a runaway process. After this collapse, the temperature rises a lot, all the other elements are ignited, and a huge explosion is induced, and this explosion leaves no remnant, meaning that the explosion will leave no black hole and no neutron star. Now, what are the effects of this pairing stability supernova on the black hole spectrum? In this picture, we see on the x-axis the initial mass of the star, mass of 0-age main sequence, and on the y-axis the mass of the produced remnant of the black hole around the neutron star for lower masses. The different colors represent different basaliticities for this mass spectrum. If you look at this region, we see this flat region in which basically the star produces a remnant with mass equal 0, meaning that no black hole and no neutron star, no remnant will be produced. This is the region in which pairing stability takes place, and the main effect on the black hole mass spectrum of this pairing stability is that a mass gap is produced in the black hole spectrum. As we can see here, this yellow band reproduces what is the mass gap, which is more or less between 70 and 130 solar masses. So from single stellar evolution, it's not actually possible to produce black holes in this mass range. But in my simulations, I actually found a way to produce such black holes and to make them merge. Here in this slide, I briefly summarize how this process works. We can see that if we have a main sequence star, mostly made of hydrogen, and a star with an already developed helium core, if these two stars merge, they will form a star with a large hydrogen envelope, a massive star with a large hydrogen envelope, but with a small helium core, because it preserves the helium core from this giant. This core can be below the pairing stability supernova threshold, but the star can be more massive thanks to the merger that happened. The star can eventually collapse into a black hole which lies in the pairing stability mass gap. And if all this process takes place inside a star cluster, this black hole then can eventually dynamically pair with another black hole and merge with gravitational wave emission. Actually, I have shown this mechanism in my paper from 2019, and some months ago, some months after the publication of my paper, the LEGO Virgo collaboration detected a binary black hole with the primary mass in the pairing stability mass gap. So I was very happy about this because my result turned out to be a prediction of this detection. Now I will show you an example of one of such systems which formed in my simulations. This is a scheme of the evolution of one of these systems. The time goes from top to the bottom. On the left branch, we can see that we start with this binary made up of two main sequence stars. One of them evolves into a giant with a developed helium core. These two stars merge, producing this giant with a larger mass, but with a small helium core, which collapses into a black hole which lies in the pairing stability mass gap. Then, thanks to dynamical interaction, this black hole pairs with these other black holes to form a binary. And thanks to further dynamical interaction, this binary hardens and merges, forming this final black hole. But how many of these black holes do I form in my simulations? Here, I show all the black holes lying in the peristability mass gap, which I form, with respect to the mass of the host star cluster. The marginal histograms show the distribution of the mass of the black hole and the mass of the star cluster, and the different colors represent different metallicities. The red one is the solar metallicity, while the blue one is the lowest metallicity that I simulated. As you can see, I forgot to say that the orange symbols represent the merging binary black holes, the black holes which are in emerging binary black holes. And as you can see from here, the merging binary black holes tend to be in more massive star clusters. And you can see that this effect is not only on merging binary black holes, but also on the whole population of black holes. In fact, if you look at this marginal histogram, you may think that the distribution is rather flat, but we actually have to compare it with this dashed gray line, which is the distribution of the simulated star clusters. Because if you recall, I simulated more less massive star clusters and less more massive star clusters. And as you can see, since the distribution of the simulated star clusters, of the initial mass of the simulated star clusters, is more steep than this distribution, this means that the more massive star clusters are more efficient in forming black holes in the peristability mass gap. In my simulations, these are very rare event. In fact, only 2% of all merging binary black holes have a member which lies in the peristability mass gap. Okay, and now I will talk about the last part of my results, which is about the formation of intermediate mass black holes in young star clusters. So let's start with the definition of what an intermediate mass black hole is. An intermediate mass black hole is a black hole which is not a stellar black hole and not a supermassive black hole. So it bridges these two different kinds of black hole, and it is defined as a black hole with mass between 10 to the second and 10 to the fifth solar masses. Currently, we lack direct electromagnetic detection of these types of black hole, and there are some candidates of them. There are also a lot of proposed mechanisms for the formation of this peculiar type of black holes. And the one that takes place in my simulation is mostly the runaway collision one, which I'll try to explain here thanks to this cartoon. So here on the left, we can see that we have a star cluster. And thanks to the dynamical friction, the most massive stars tend to fall inside the core of the star cluster. Inside this core, these very massive stars are confined, and thanks to their stronger gravitational pull, they are very likely to collide together. And eventually, they will all collide together, or most of them will collide, forming a very massive star, which then can undergo direct collapse and form an intermediate mass black hole. So this is the process that takes place inside my simulations. And the most massive black hole that I am able to form has mass of 438 solar masses. As you can see from this scheme, the formation of this very massive black hole, in this formation, 10 stars, a total of 10 stars, take part, and a huge number of mergers and dynamical interaction is needed to actually form this type of black hole. Intermediate mass black holes are very rare objects in my simulations. In fact, just 0.2% of all the formed black holes are intermediate mass black holes. And for all of them, the formation happens in the very first million years of my simulations, more or less in the first 5 million years. We also know that less massive intermediate mass black holes are more likely to form. So we're able to form more black holes closer to 100 solar masses than very massive ones. This is the distribution of the masses of the intermediate mass black hole that form in producing the form of a violin plot for the 3 different metallicities that I simulated. As you can see, the formation of intermediate mass black hole is very sensitive to stellar metallicity. In fact, at a larger metallicity, which is the solar metallicity, I form only 4 intermediate mass black holes. While at lower metallicities, I'm able to form more intermediate mass black holes and also more massive intermediate mass black holes. So to better check this, I have produced a table in which I show the efficiency of the formation of intermediate mass black hole for my star clusters. So as I stated before, all of my, if I take into account all my simulations, roughly 2% of my star clusters form an intermediate mass black hole, and a very small fraction is able to form 2 intermediate mass black holes. But now let's divide all my simulations into 3 different subsets, one for each metallicity. As we can see, the percentage of star clusters which are able to form intermediate mass black holes grows as metallicity decreases. So lower metallicity is much more effective, and we go from 0.15% at solar metallicity up to 3.25% at the lowest possible metallicity. And this effect is also visible for the rare star clusters which form 2 intermediate mass black holes. Then I've also produced 3 different subsets, not for metallicity, but for the initial mass of the star clusters, going from the least massive star clusters that I simulated to the most massive ones. And in this case, we can see that the most massive star clusters are much more efficient than less massive star clusters in forming binary black hole, going from 1 to more than 7% for one intermediate mass black hole. And here as well, we can observe this for the 2 intermediate mass black hole case. So the formation of intermediate mass black hole is even more sensitive to the initial mass of the star clusters than metallicity. And finally, I also wanted to check if the intermediate mass black hole have any effects on the dynamical evolution of the star cluster. And to do so, I have produced this plot which shows the evolution of the Lagrangian radii of the star clusters, which are the radii which include the 10, the 30, the 50, and the 70% of the total mass of the star cluster. The solid line represents star cluster with intermediate mass black holes, while the dashed lines represent the star clusters without intermediate mass black holes. As we can see, especially in the first part of my simulations, the star clusters which contain intermediate mass black hole tend to expand more. And this effect is more visible in the larger Lagrangian radii. In fact, the 70% one is much more distant from the dashed line, meaning that this expansion is more effective in the outer parts of the star clusters, which will tend to expand more if an intermediate mass black hole is formed in the star cluster. After some time, we also see that 10% Lagrangian radii tends to overlap with the one of the star clusters without intermediate mass black hole. And from that moment, it starts to behave more or less the same. And we expect that this will happen also for larger Lagrangian radii as well. The reason for this expansion is mainly due to the dynamical heating exerted by intermediate mass black holes, which will tend to give energy to the least massive stars and send them in the hull of the star cluster. So these are the take-home messages from my PhD thesis. First of all, I found out that dynamics strongly affect the properties of merging system, increasing the mass of the mergers and lowering the mass ratios. Then we also know that the formation of binary black holes with the members in the peristability mass gap is possible, and we also know that they can merge, and this was also confirmed by the detection we got by LIGO and Virgo. We know that dynamics washes out the metallicity dependence on merger efficiency, dramatically boosting the efficiency at larger metallicities. And finally, we know that intermediate mass black holes can form mainly through runaway collision, and this mechanism is very sensitive to metallicity and to star cluster mass. Thanks for your attention.
Thank you, Ugo. Questions from Rosario, for example?
Yes, Ugo, I have a very basic question. Which is the role of the metallicity during the merging?
During the merging, there's actually no role because the black holes are not sensitive to the metallicity. But the metallicity has a huge impact in the evolution of the progenitors of the black holes because it increases the efficiency of mass wind. So at larger metallicity, stellar winds are much more powerful, stars lose more mass, and so you are not able to form the same number of black hole, and also the black hole as massive as what happens in lower metallicities.
Okay, it is linked so to the wind of the stars.
Basically, yes, that is where the metallicity
The second
impacts
question,
more.
the second question is about the common envelope. In your code, so you used a receipt for the spiraline.
Yes, basically we use a formalism for the common envelope, which is called the alpha lambda formalism, in which you have basically these parameters which describe the geometry of the system and how much of the energy of the stars inside the common envelope is given to the common envelope. And the outcomes of the common envelope may either be that the common envelope is ejected, so the binary shrinks, and then they can eventually form a binary black hole, which can merge, or the envelope is not ejected, and you end up merging the stars inside the common envelope, and this event is not interesting for gravitational wave detections.
And the ejected matter, in the case of the ejected matter, this not influence the evolution of the system.
Well, it influences the evolution in terms of dynamics, but in my code, that mass is removed from the system, so it just affects the properties of the binary because you lose some of the mass that you had before. But other particles just feel a sudden loss of mass from the system.
Okay, thank you, Ugo.
You're welcome.
Fabio?
Yes. Well, first of all, congratulations. This is very impressive work.
Thank you.
So I have many questions, but I will ask you maybe a couple of them. So you mentioned at some point that only a very small fraction of your binary black holes merge inside the cluster, and it wasn't clear to me whether you actually take into account relativistic corrections to the motion for in your simulations during small body, small number, during dynamical interactions. There was a number of papers, recent papers, that show that if you do include this gravitational during these gravitational interactions, relativistic corrections, then the number of in-cluster mergers increases significantly and becomes even the larger contribution to the production of binary black hole mergers from dense clusters. So I wonder, how do you implement the relativistic corrections in your simulations, and whether these are actually taken into account during the simulation? Okay, so actually my code does not include post-Newtonian terms, so it's just Newtonian dynamics, but the binary made up of contact objects are evolved also with the gravitational wave loss, energy loss, thanks to the formula by Peters. But I'm aware of the fact that relativistic correction can boost the number of mergers, and unfortunately I didn't include them in my simulation run. It would be interesting to find a way to properly include them and to see what's the effect on my merging binary black holes. Yeah, that would, I think, be very interesting. I think you would get many more in cluster mergers in these simulations. So another question about more general question about young star clusters. If you could tell a little bit more about the relation between young clusters and the other type of clusters. It wasn't clear whether maybe young, if you mean for young cluster systems that eventually become open clusters, globular clusters, or is there any connection between young clusters and all the other type of clusters that we observe in the universe?
And it's actually an important question, because we don't know if the most massive young clusters which we see now can eventually become like the observed globular clusters, but most of the ones that I simulated have low masses, so they basically become more like open clusters during the dynamical evolution, because they lose mass and they expand. And yes, this is the main relation between young star cluster and open and globular star clusters. I'm aware of the fact that also OB associations exist. I know about the recent paper that you pointed at me about the fact that the OB associations may not come from the evolution of young star clusters, but they may evolve in isolation. And thanks for pointing me at that papers. I will take into account for my future studies.
Yeah. So yeah, I think that's important to point out, right? Because actually, when observations of massive stars show that most of them are not really in clusters, but they are in associations where stars are not really bound to each other, and that's the majority of them. So I think that's an important point. But the last question was about again quite general, but if you can tell us a little bit more about the uncertainties, the main uncertainties in your models. You mentioned already the common envelope treatment in your simulations. So maybe you could tell us what are the main uncertainties there. I understand the parameters in the alpha lambda model, but there are also uncertainties. So maybe you want to mention some of them. And
Sure.
Also, I was wondering about what goes into the code when you merge two stars and then evolve the merged star, and yeah, how does that work?
Sure. I would say that there are three main uncertainties in my models, one of which is the common envelope parameters that you mentioned, because they were actually calibrated by trying to match observables of LEGO Virgo from population synthesis simulations. And we still not know what the proper values of these alpha and lambda parameters would be, because we currently lack realistic simulations of the common envelope. Another possible uncertainty is the kick, which is received by the black holes and the neutron stars after their formation, because we adopted a kick which is drawn from a Maxwellian distribution with velocity of 35 kilometers per second. It's very difficult actually to adopt a proper kick model, because we lack observations of kick, and we have to rely on the very few observations of neutron stars, which are different objects, and we can just assume that black holes behave similarly, with the only difference that black holes have a fallback correction, which quenches the entity of the kick. And so luckily they are less affected by the kick with respect to neutron stars. And the third uncertainty lies in the how the code treats the mergers, because it basically I assume that when a star merges with a compact object, all the mass of the star is dissipated, so there is no accretion on the black hole. And not only this, but also when two stars merge, the code calculates a fraction of the mass which is lost, and this depends on the orbital parameters of the star, mainly on the eccentricity. And it would be nice to better calibrate these parameters as well.
Can you envision any way of doing that, this calibration, like how to improve these models?
Well, I guess that hydrodynamical simulations of colliding stars would be one of the best ways. Actually, there is a in my group a person which is trying to do this with a code called Star Smasher. I think that it can lead to very interesting results.
Okay. Thanks, Hugo. That was my last question.
By the way, if you have more questions, just drop me an email. It would be nice to discuss.
Yeah, of course, I will. Thanks.
Thank you. You're welcome.
I have a couple of very naive questions. Sorry for not being an expert in this. Just a technical one. You mentioned your MOPSI code dealing with stellar evolution. This stellar evolution is treated regardless the environment in which each star is evolving. Is this correct?
Yes, but this code is coupled with Embody6 code, which actually includes gravity. So during the evolution of the gravity of each particle, the gravity part calls the functions from the stellar evolution part and tries to perform it in the more consistent possible way.
Okay. I've seen that in your merger tree, when you merge black holes, the total mass of the final black hole is just the sum of the two masses of the black holes, while I'm not sure to remember correctly, the binary black hole merging after the release of gravitational waves, the total mass is not the sum of the two masses. Is that something which comes to the code, or is just a matter of having a rough estimate of the final black hole mass?
I mean, we just didn't take into account the mass energy loss due to gravitational wave emission, but I'm aware of the fact that some of the mass is lost after the merger.
Okay, I have another final, extremely naive question, and you have dealt the problem of these binary black hole formation in a more general sense in a quite well-defined ambient, which is these very massive star clusters still forming stars. Probably these are dynamically constrained or not too difficult to handle. I was thinking to different environments like star-bursting galaxies, in which masses of gas are converted into stars in relatively small time scales, in a very, say, orders of magnitude larger scales, in the sense that 2 or 3 orders of magnitude more gas is involved in this star formation. Is your method, can your method be applied also in less controlled, dynamically controlled environments, or it is just related to ambient in which you can handle gravity and evolution of individual objects?
Well, including the gas hydrodynamics in my simulations would be very dynamically expensive. There are some people who try to do so. For example, Portuguese Swart with its code Amuse, which tries to couple gravity codes with hydrodynamical ones, but it's very expensive to run simulations of both accurate dynamics and gas hydrodynamics, especially if you want to take into account large scale sizes like the ones of starbursting galaxies. So I'd say that my code would not be the best one to simulate the star forming regions of galaxies, but you know, it's always possible to try.
Okay, thanks. I have no further questions. I think that Thank you, Ugo. We can move to the last presentation from Arianna.